Hi guys, welcome back to my channel Programming with Pirai. In this video, we are going to see about Leetcode question number 501. Find mode in binary search tree. Given the root of a binary search tree with duplicates, return all the modes, that is, most frequently occurred element in it. So they are asking us to find element which occurs most, okay? And if the tree has more than one mode, return them in any order. Okay, so what they are stating? So they are stating that they will give a BST, a binary search tree. What is your binary search tree? Its left side will be what? Lesser than the node or equal to the node, and right side will be what? Greater than or equal to the node. Okay, for example, if I take this tree, all the left subtree will have what? Less than or equal to 3. All the right subtree will have what? A greater than or equal to 3. Like that. Which is the binary search tree, right? Okay, now they are asking us to find the most frequent element. So how to find it? Okay, so for example, in this tree, if I find the most frequent element, I can say, first of all, I want the count of each and every element, right? So 1 occurred how many times? 1 occurred only one time. 2 occurred I think 5 times. Okay, 3 occurred 2 times, and 4 occurred 1 time, and 5 occurred 1 time. So I can say from this 2 occurs most time. So I will return what? I will return the value as what? Only 2, because 2 is the value that occurs, right? Occurs more time while comparing the other elements, right? So I return 2. Okay, take for example, if I have something like 1, here also 1, and here it is 2, and here it is 2. So it is a valid binary search tree, and here I can say 1 also 2, and 2 also 2. So they both occurred equal number of times, right? And also they are the maximum. So I'll return what? 1, 2. You can also return what? 2, 1 also. Order doesn't matter. Okay, only the elements matter. Now, how to do this? Okay, what we are doing here, we are counting, right? We are counting each and individual elements. So I can do a BFS or a DFS traversal in the given tree. Then I want to just take the count of them, right? I will take the count of them. Simple. And I will return what is the maximum count. I will return what? The maximum count. That's it. So let us understand by taking the hash map solution. This is a hash map, okay? Now tell me, first of all, I can do any order traversal, right? If I do any order traversal, this hash map will be filled with like what? First of all, 1 is 1, then 2 is 5, then 3 is 2, then 4 is 1, then 5 is 1. Now it's time to take the maximum among this. So what is the maximum among this? I can say the maximum among this is this 5. This 5 is the maximum value, right? So I will return what? I will return 2. That's it. Can you understand this? Okay, now tell me the time and space complexity for this solution. I can say my time complexity will be O of n because I'm traversing each and every node, and also log n because I'm taking it into the hash data structure, right? Hash map. So hash map at most time complexity it takes what? A log n time. That's why a log n. And space complexity will be what? O of I'm taking each and every node count. At most it will be what? A n plus. If I do a recursion approach, like a DFS approach, then it takes what? A height, right? Height of this tree will be also the space, right? For the stack, for the internal stack. So I can say n plus height of this tree. So this is the time and space complexity. So whether we can optimize this code. Okay, let us understand how to optimize it. Finally, what are the properties of this binary search tree? So I can say the properties of binary search tree is, first of all, the roots value is always greater than, or we can say the left subtree value will be always less than or equal to the node's value, right? And for the right subtree, I can say it is ultimately it is ulta, which means what? It is reversed. So it will be like this. So I can say this is the one property. Okay. Whether we have another property? Yes, we have. When we traverse in order, we get what? We get a sorted array, like a sorted. We will get in a sorted order. Yes, while traversing in order, we get a sorted order. So can we use this to find the count of each and every elements and update in our result? Can you understand this? Okay. If I give you a simple representation like array. It is like 1, 1, 2, 2, 2, then 3, 3. Now, what would you do? You would take this as our one pointer. Then I will check whether this is the starting net, right? So I will conformly go here. and I will check whether this 1 is equal to this 1. Yes, then I will increment my count, right? Again, I will go to this 2. Now 2 is not equal to 1. So up to this, the range of 1, right? Again, I will traverse this, and when I go to this, I can say this 3 is not equal to 2. So I will take this as our count. Can you understand this? So this is a sorted array approach. In array, we will do like this, right? So similarly, this is the same step we are going to do in this tree also when we are doing a in-order traversal. Hope you understand this. Now let us begin. Okay, now we are going to do what? A in-order traversal, right? Okay, for in-order traversal, what is my property is left, then right, sorry, root, then right? So this is the in-order traversal. Okay, first of all, going to the leftmost value, right? Okay, going to the leftmost value. Go, and go. Now it is what? A null. Okay, when null, I will return back, right? So now I will return back to the root. Okay, so what are the things we want? We want what is the previous element? We want to keep track on the previous element, right? So we enter previous element. Okay, now again we want the current maximum, right? We want to keep track on the maximum. So I will take F for the keep track on maximum, and also I want the result as what? What is the element that has the same value? Right, so we want the element which has the same value. So sorry, the maximum count. So I will take that in the result. Fine. Now what else we want? We want another value called a count. Why we want this count? Because we want to take the count of how many elements are same value, right? Right. So I will take the count. Okay. Now fine. Now initially I set this as -1, previous is -1, and count is 0, maximum is 0, and result is also a empty list. Okay, fine. Now let us get started. Now it is what? A 1. So I can say 1. So it is not equal to a pre, but pre is what? Pre is -1, which means what? We didn't have any element in our previous, right? So I can say count will be 1, and my maximum also updated as what? 1, because count is 1, right? So maximum is updated as 1, and the result will be updated as what? 1. Because this node's value is what? 1, right? And the previous will be what? 1. Again, I will go to the right side. Okay, now backtrack. And again backtrack. By backtrack, it is what? A 2. So root is 2. So I can say previous is not equal to 2. Previous is not equal to 2. So what else we should do? We should take the count again to 1. Because the previous count is over. Now we want to take the 2 as our consideration. Okay, now m is equal to what? M is equal to also 1. Because 1 and 1 maximum is 1 only. Okay. Now again in result I will add extra as comma 2, because both 1 and this 2 has what? Equal value, right? It is not maximum. It is equal value. So I will take this 1 and 2. Can you understand this? Yes. Now again I will go to the right side. It is null. So I will return. Okay. Again I will, while backtracking, it comes to this 2. Now again I forgot to update this as 2. While I am at this node, after backtracking, this will be updated as what? 3 is updated as 2. Okay. Now, when I am standing here, I am going to check whether the previous element is also equal. Yes, the previous element is equal. So I will increment my count to what? 2. So maximum will be updated as 2. So I want to delete this entire list and create a new list called what? Just insert 2 here. Can you understand this? Because the 2 has a higher count than the previous values. So I will delete them all, and I will take only 2 alone. Fine. Now again I will go to the right side. Okay. Now again go to the left side is null. Again go back. Again it is what? A root is what? 2. So previous is 2. Again it is 2. So I can say what? Increment our count to 3. So max becomes 3, and this will be what? Become what? Again 2. Can you understand this? Yes. Now again I will go to the right side. Okay. Backtrack. Again here also backtrack. Again here also backtrack. It is also what? It is also 2. Now previous is 2, current is also 2, it will be 4. Okay, and maximum will be updated to what? 4. Again here also 2 will be not changed. As it is. Instead of deleting and replacing it, keep as it is. Simple. Again I will go to the right side. Okay, here I go to the left side. Again backtrack. Now it is what? 2. Previous is also what? 2. So I can say count will becomes 5. Okay, now maximum will becomes also 5. Yes. Again this result will be as it is, 2 as it is. Okay, now again I will go to the right side. Again I go to the left side. Again backtrack. Here comes what? A value 3, which is not equal to the 2, right? So I want to change this count as what? Again back to 1. again back to 1, because now I am going to start with a new value, right? So it will be 1 and the maximum remains 5 itself, because 5 is maximum than 1, right? So it remains 5 itself, and whether our current count is greater than the previous maximum, no, right? Previous maximum is 5. So I don't want to update anything in our result. Result remains as it is. Okay, now 3 will be updated as what? 3. Okay, I go to the right side, it is also null, backtrack, now it comes to what? Comes to this 3. Okay, again, pre and current value is 3. Okay, now I want to do what? I want to increment my count. Again, it is not greater than the n or equal to the n. So I cannot include this and I cannot update the list, right? So I want to go to what? Go to the right side, again go to the left side. Here it's null, again go here. Now it is what? 4. 4 is not equal to 3, right? Right? So I will make this count as what? 1 again. And I want to check whether 1 is greater than or equal to this 5. No. So I don't want to do anything. And I will update this 3 as what? 4. Can you understand this? Then I will go to this right. Then again go to this left. So it is null. Again go up. It is what? 5 now. So I again make this count as what? 1. And I will check whether 1 is greater than 5 or equal to 5. No. Right? So I don't want to do anything. And I make this 3 as 5. Okay, I go to this right, there is no more. Backtrack. So at final, what is our result? Result is only 2. So what are we adding? We are just checking if m is equal to our count. Sorry, yes, our count. If it is so, then I want to add that current element into our result. Okay, else we can meet some condition like count is greater than m. At that time, what we do? We take that itself our result. So we take that itself our result. Hope you understand this, right? So these are the 2 conditions we want to focus on. So we are going to do in our traversal, and we are going to take the maximum along the sorted path. Right? Now, what is the time complexity? So I can say this is the most optimal solution. Okay, tell me what is the time complexity. I can say my time complexity will be my time complexity will be O of n, because I am traversing each and every node only one time. And what is the space complexity? It is O of h. It only take what? It only take this whole tree's height, because we are just doing what? A recursion, right? A recursion. So it creates what? A recursion stack, and that's why we get what? O of h. Hope you understand this, right? Now let us see the code. See here, this is the code. For first step, it is what? A dictionary. I'm defining a dictionary. Then I'm just traversing simply, and I'm just putting the value inside my dictionary and taking the count. At last, result is equal to empty list. M is equal to 0. If I in d dot keys of, if d of I is greater than m, then what should I do? M is equal to d of I, and result is equal to take that value alone as our answer. Can you understand this? Okay, if it is equal to, then I want to take that I value, that key value as our answer. That also one of my answer, right? And then I want to return it. Let me submit it. Yes, it is submitted successfully. Now let us see the optimal solution. See here, count m is equal to 0, Now result is equal to empty list. Now I am taking the pre as what? And none. Here I took what? Pre as none. But in real time, in the drawing expression, I took -1, right? But in real time, they have given what? Minus 10 power 5 is less than or equal to node dot value, and less than or equal to 10 power 5. That's why I'm taking what? I'm taking the pre as none initially. Then I will take that pre as the values. Okay, or you can take the pre as what? Float of infinity or int max, int min, like that. Whatever. It should be what? It should be not equal to the any of the roots value. It should be out of the range of the roots value, right? Okay, now def DFS of root non-local, these 4 variables. What are they? Pre, count, m, result. I told this in the drawing example, right? Now, if not root, then I should return. And then I am doing left sub tree traversal. After that, I am doing what? If pre is equal to the roots dot value, which means what? The previous element and the current element is equal, then what should I do? I should increment our count. Else, what should I do? I should make the pre as what? Roots value, and the count as what? A 1. Can you understand this? Yes. Now, if the count is greater than m, then what should I do? I should assign that count as our maximum, and also take that alone as our result. Right? Else, if m is equal to the count, which means what? We want to take that also in our result. That's also one of our result. Maybe, right? Okay, and then I'm doing what? Right subtree traversal. So this is the in order traversal. Inside it, I am putting a couple of just a if condition, right? Okay, now I'm just calling that function, then returning the result. Let me submit it. Yes, it is submitted successfully. Thank you.